second part of the supersonic diamond aerofoil. And in the second part, we will talk about the measurement. First, let's talk about the pressure reading. On the right-hand side, we can see 3 manometers. Basically, they are 3 U-shaped tubes in a field with mercury. Now, let's represent the middle one. And here's a conceptual view. And we can see the U-shaped tube, and it's filled with mercury. The left tube has higher level than the right one, and there's a ruler in the center, and the ruler is in inch. The left-hand tube connects to the wind tunnel pressure tap, and the right tube is open to the room. So the right-hand side senses atmospheric pressure, but the left-hand side senses pressure in the pressure tap. Now the question is, in such a scenario, which side has higher pressure? I give you a few seconds to think. Yes, the right-hand side, the room has higher pressure. Because it's higher pressure, it pushes mercury into the left-hand tube, right? Okay, now let's do the reading. The left-hand side has a height of H1, the right-hand side has a reading of H2. Okay, so H1 larger than H2, which means the pressure on the left is less than P atmosphere. Okay, then we can get the pressure difference, which can be calculated as rho GH 1 minus H2. Okay, so we need to make use of the height difference. This only gives you the pressure difference. Now in the opposite, if the H1 is less than H2, which means pressure in the wind tunnel is larger than the atmosphere, than the room pressure, but still the pressure difference is calculated as rho g, but because H2 is larger, we use H2 minus H1. And the pressure of mercury is known, and it's indicated in here. So in order to get absolute pressure of the wind tunnel, you need to measure the atmospheric pressure. So then you can get the pressure, absolute pressure, in the wind tunnel. Let's talk about the angle of attack. Here is a close-up view of the test section. And in the measurement, we are not going to measure only one angle, but a range of angles. So the angle of attack, we will adjust from minus 5 degrees to 5 degrees, positive 5 degrees, and in total, we are going to test 7 cases. Now it's a time to see the Schlieren visualization. The flow is from left to right. This is actual flow happening in the wind tunnel, and the aerofoil is indicated. We can now see the wake start to develop, so it's capturing the startup procedure of this wind tunnel. Now the valve is gradually being opened. The wake is developing. Now it's still not supersonic, and gradually the speed accelerates. We can see the disturbance on the aerofoil already. So quickly it will become supersonic, and you will see the shockwave. Now it's transonic. You can see the shockwave is on the aerofoil, and also you can see the streaks in the free stream, and the shockwave becomes stronger. This is typical transonic flow. And okay, now we have the normal shock. It's about to fully start up, and the normal shockwave becomes attached. Okay, so this is a steady flow we are looking at, and we have the leading shockwaves, expansion fan, and also the shockwaves at the trailing edge, and also the wake of the flow. So this is what you can expect in the wind tunnel. Just to mention, the angle of attack now is 0 degrees. So there's no angle of attack. Okay, So now let's study the flow in a bit more detail. First of all, we see the shock wave from the leading edge, and because there is expansion when the flow passes a tip, so we can see the expansion fan. And you can see on the top part, the expansion fan is bright, but on the lower side, the expansion fan is dark. This is because of the knife edge is placed horizontally, so they show up as different colors. And if we move further downstream, we can see the shock wave from the trailing edge and also the wake of the aerofoil. So that's basically the four important phenomena in the test section. Okay, so basically in your coursework, you have to measure the angles of the shock wave and also the expansion. And it will be interesting to see how the flow field will respond to the different angle of attack when you change angle of attack. So you can see the flow does change a lot, and similarly, you should be able to measure the angles and compare with your simulation and theoretical calculation. And it would be interesting to point out that when the angle of attack is very large, for example, positive 5, you can see the shock wave boundary interaction over the floor. That's a very interesting phenomenon and also important phenomenon in supersonic aerodynamics. If you have interest, you can read some other literatures to get detailed understanding.